The electric field of a point charge is given by this relationship. It is a vector, and so we need to indicate both a size and a direction. And if we assume a positive charge here of size q, then we can write it as kq over r squared, given the magnitude, and the direction is r hat. Okay. Now the question is, well, what happens when we have an electric field from a series of point charges or a series of sources? And just like any other vector, we just add up the vector components. And so suppose we have this case. We have a negative charge of the same size, only negative, and let's position a coordinate system such that our x-axis points or bisects the two, and our y-axis goes through the two. This is our y-axis, choosing up to be positive. Okay. If these are really close together compared to the distances we're measuring, we call this a dipole, and it has really important implications for chemistry and other fields of science because most molecules have slight polarization to their charge. Like water is a polarized molecule. It's got a slight heavy positive side and a slight negative side of equal magnitude, and therefore it interacts with other charged particles through their electric fields. And so this becomes a really good model for them. So let's go ahead and start and try and say, okay, well, what is the electric field right there due to these two charges? Well, first let's define a distance between them. We'll call it s. Okay. And then this position here will be a distance y up from our origin. Okay. So by plugging this in now, I'm going to write E now of this whole thing is going to be, okay, the electric field from this one is upward, so I'll indicate that with the sign. So it's going to be a plus K, Q, and its distance is just this much from here, from the source to where I'm measuring, so that's going to be y minus half s, because the charge is already halfway s, half of s up the y-axis. So this is going to be now y minus s over 2, and I have to square it. And that's going to be in the upwards direction. Okay. Now before I write that upwards direction, I'm going to go and do the next piece, because the next piece has a downward electric field. At this point, this negative charge has fields pointing towards it. And so we get a negative, but otherwise it's the same size of charge, yet its distance is slightly farther, this time by plus s over 2. Okay, so it's a y plus s over 2. And now I can write my up or y hat direction. Okay, so let's focus on just the size now. We'll just note that our reference direction is up for these signs here. Okay, so in doing so, let's try and simplify this a bit. We've got a kq that's the same on both sides, and we'll be left with a 1 over y minus s over 2 squared, subtract 1 over y plus. Let's get a common denominator, multiply this side by this denominator. That would give us a y. I'm going to go and factor that out, so we get a y squared plus an s over 2 squared, and plus the cross term, plus a 2y s over 2. Okay, so that's this thing multiplied to this top and bottom, so I get that up top. Alright, the bottom is this times this. I'll just leave those together. It'll be a little bit simpler as we move further on. Okay. So this denominator became the product of these two, which means the top, which used to be 1, is multiplied just by this, which I factored out. We're doing the same thing to this side, so I take this, multiply it by this, which is the same denominator, but now the numerator, which again was 1 because I pulled the kq out, I take 1 times the square of this, which if I factor out is the same thing, except in that final cross term, I end up with a minus. So there's a minus here, so a minus, and this whole thing, y squared plus s over 2 squared minus 2y s over 2. I'm going to close the parentheses. And again, I'll hold off on the direction. We'll just note right now that the directions are all up. Okay. Alright, well that looks pretty ugly, but thankfully I see that we have a cancellation here cancellation here, and then we have cancellation there, cancellation there. Then we're left with the ys minus a minus ys. So we get ys plus ys. We end up with a 2kqys over y minus s over 2 squared, y plus s over 2 squared. Alright, that doesn't look terribly good either, but now let's go ahead and consider a good approximation. If I'm looking at a molecule, even if I'm a micron away, molecules are teeny. Molecules are super small, nanometer size. And so if I'm even a micron away, then the distance between them, the two charged particles in a molecule, are teeny. S is teeny compared to any y value I would measure. Okay, so if I consider that y is much bigger, y is much bigger than s. Okay, so I'm really far away, way up here or way down here. I'm looking really far away from this thing. Then I'd say that if y is huge, then y minus s is small, is basically y. I like to say this is a million minus 1 is basically a million. Okay, so I can say that this becomes a y squared. So this basically is ignored. Same thing here. A million plus 1 is basically a million. So I get another y squared. My 2kqys at the top. Alright? Well, I can cancel that y with one of those, and I'm left with a 2kqs over y cubed. That is the electric field that I would measure along the axis of a dipole, a molecule or a pair of charges that are opposite in sign but equal in magnitude and spaced a distance s apart. Okay, now, generally that distance s apart might be pretty hard to measure, but something that we could qualify since the size of the charge is a product of the molecule, and the separation is a product of the molecule, or it's dependent on the molecule, then the product of q times s is just a molecular parameter, and we often combine those to say that the electric field is 2k, and we give that something, a variable p called the dipole moment, which we can carry a direction with it. Remember, our direction was up this whole time. We can say that p points from the negative to the positive, which in this case is up. And our derivation was assuming the positive was higher than the negative. And so by defining p as being the size of the charge times the separation and points from the negative to the positive, okay, then we can indicate both the size of this as well as its direction. So that is the electric field of a dipole along the axis of the dipole.